Everybody, this is Dr. Nigro. This screencast is going to look specifically at inelastic collisions. If you need to go back and review collisions in general and recoil, please go look at that particular screencast. All right. So we need to define an inelastic collision. So an inelastic collision is not a recoil collision. All right. An inelastic collision occurs when two objects, whoops, that are initially moving separately collide and stick. All right, these objects move together after the collision. All right, so the inelastic collision occurs when these two objects are moving separately. Now, one object doesn't have to be moving. All right, one object can be moving towards another. Both objects could be moving towards each other, or one object is chasing another. Those are kind of the options for the before. All right, the key is that once the collision happens, the two objects are stuck together. They get tangled up somehow, and they move together as a single unit after the collision. All right, so an example of some sort of inelastic collision, a car accident where the two cars are tangled up. They somehow, the bumpers get bound up together or something, but they move together after that collision. That would be an example of an inelastic collision. All right. Now, with an inelastic collision, all right, momentum, let me spell that out instead of writing a P, is conserved, just like we saw with our recoil collision. So that is also important. All right. As I said before, when we investigate collisions, drawing diagrams are really important, showing the before and the after. We need to monitor direction of travel. And if we know velocity and mass, that's important to include too. All right. Remember, left is negative, right is going to be positive. All right. So let's look at our situation. All right, we have two carts, cart A and B, and are sitting on a frictionless track. Each cart has a mass of 1 kilogram, and cart A is moving with a velocity of 2 meters per second to the right. It collides and sticks to cart B, which is initially at rest. The two carts move with a velocity of 1 meter per second to the right after the collision. Was momentum conserved? All right, so let's start with our diagram. We've got cart A. All right, and it tells us it's moving to the right at 2 meters per second. All right, and out in front of it is cart B, which is not moving according to the problem. Now, after the collision, it tells us that cart A collides with and sticks, so that's what my little squiggle means, that they're moving together, with cart B, and now the two carts are moving together at 1 meter per second, but still to the right. All right, so to determine if momentum is conserved, we need to figure out the momentum of each cart before, the momentum of the combined carts after, and then we need to see if the before equals the after. All right, so let's start with cart A before. All right, we have a mass of 1 kilogram, and we're moving to the right with a velocity of 2 meters per second. All right, so the momentum of cart A is equal to its mass times its velocity. So 1 kilogram times 2 meters per second gives us a momentum value of 2 kilograms times meters per second. All right, so we've got a positive 2 kilograms times meters per second for cart A's initial momentum. All right, for cart B, it's also got a mass of 1 kilogram, but it is at rest, so its velocity is 0. So the momentum of B is going to be equal to its mass times velocity, and in this case, that's 1 kilogram times a velocity value of 0. So our momentum is 0. Easy enough. All right, now let's look at what happens after All right, because this is an inelastic collision, carts A and B move as a single unit after the collision, which we can call cart AB. All right, we need to determine the total mass of the two carts and then a single velocity for the combined object. All right, so the mass of A plus the mass of B is going to give us the mass of this combined AB cart. All right, so we know that cart A was 1 kilogram. We know that cart B was 1 kilogram. So the total mass here is going to be 2 kilograms. All right, now the problem told us that the velocity of the two carts after the collision was 1 meter per second to the right. All right, so the momentum of this combined cart AB is going to be equal to its mass times velocity. So we have 2 kilograms times 1 meter per second, and we're going to get a momentum of 2 kilograms times a meter per second. All right, so 2 kilograms times a meter per second for that combined momentum. All right, now to check for conservation. All right, for cart A, if we look back, we see that we had a momentum of 2 kilograms times meters per second initially. All right, and cart B was not moving, so it had 0 momentum. After, for our combined cart, we found that we had a momentum of 2 kilograms times a meter per second. And if we look, the before does equal the after. All right, so was momentum conserved? Yes, because the momentum before equals the momentum after. Okay? All right, so that's proving that momentum was conserved. Now we're going to try something a little bit different. So situation 2 is a different type of question. All right, we're still going to have our two carts, A and B, sitting on our frictionless track. They still each will have a mass of 1 kilogram. All right, cart A is moving with a velocity of 2 meters per second to the right and collides and sticks to cart B, there's that word sticks, which is initially moving with a speed of 1 meter per second to the left towards cart A. What is the final velocity of the two carts together? So this is going to be a little bit different. All right, we always start with our diagrams. So we've got cart A moving at 2 meters per second to the right. Right, and somewhere out in front of it is cart B, but cart B is moving 1 meter per second to the left towards cart A. So this would be like a head-on collision. All right, when that collision occurs, A and B stick together. All right, now we don't know which direction they're moving. They could be moving to the right, or they could be moving to the left. We're going to need to use math to figure that out, and then we'll come back to our diagram and fix the after, okay? All right, so let's start with our momentum values for before. All right, so for cart A, 1 kilogram and moving at 2 meters per second to the right. So our momentum for A is mass times velocity, so 1 kilogram times 2 meters per second gives us a momentum of 2 kilograms times a meter per second. All right, so 2 kilograms times meters per second. All right, for cart B, also 1 kilogram, but it's moving to the left, so negative 1 meter per second. All right, so for momentum of B, mass times velocity equals 1 kilogram times a negative 1 meter per second. All right, so our momentum here will be a negative 1 kilograms times meters per second. All right, so negative 1 kilogram meter per second. So that's before. After the collision, the two carts are moving together, so the mass of the combined cart is equal to the sum of those two mass values. And in this case, it's 1 kilogram plus 1 kilogram, or 2 kilograms total. All right, so our total mass is 2 kilograms. All right, now this time we do not know this value, so we cannot calculate that momentum. All right, we know that the momentum of AB should be mass times velocity, and in this case, we know the mass is 2 kilograms, but our velocity of that combined cart is unknown. So this is all that we can write in terms of our after collision momentum. All right, so if we come down to our table here looking at conservation, we're going to fill in what we do know. All right, we know that cart A's momentum before was 2 kilograms times a meter per second. And we know that cart B was a negative 1 kilogram times a meter per second. We know that afterwards, whoops, the momentum is equal to 2 kilograms times our unknown velocity, AB. All right, so we're going to add the two together on the left side of the equal sign. So 2 plus negative 1. So I'm going to get 1 kilogram times a meter per second. And that's going to be equal to 2 kilograms times our unknown, VAB. All right, so I want to solve for this velocity value. So I'm going to divide both sides by 2 kilograms. It's going to cancel. I'm going to come over here and divide by 2 kilograms. All right, the kilograms are going to cancel, and I end up with 1/2 meter per second. All right, so the velocity value after the collision must have been 1/2 or 0.5 meters per second. All right, now note that the value is positive, which means that that object, that combined object, is moving to the right. Right, so if we go back up to our diagram, right, we can erase our left arrow because it's not moving in that direction. Instead, we can write 0.5 meters per second on our right-hand arrow, meaning that the objects, when they collide and stick, are still moving to the right. Okay? Now, I know that's a little different, and we're going to do some practice in class, but it's another way to use some of our collision information. Okay?